Okay, so we are doing the IBDP SL portion of the enthalpy, that is chapter number 5. So in this part, we have to know that the enthalpy is what? Enthalpy is nothing but is the heat content of a system, right? Now, if you're seeing any heat content of a system, right? There can be two kinds of reactions, right? One is called as the exothermic reaction, right? In an exothermic reaction, what happens? The reactant gives out heat and the product is formed, right? So reactant gives out product plus heat, right? And we are doing what? We are trying to find out what? We are trying to find out over here that we are connecting this with this over here to here, right? Here to here. Hmm. Now, what is the activation energy? Now write down this, right? Activation energy is a reactant to the top of the hill. Please try to mention this, right? Reactant to the top of the hill, to the top of the hill. What is the delta H? Delta H is reactant to the product, right? This reactant to the product, right? This is the delta H you're having, right? Fine. So in the exothermic reaction, we are seeing what? Reactant is having a higher energy than the product, right? Reactant is having a higher energy than the product, right? Always. And the product is more stable than the reactant. Now, if you see a endothermic reaction, right? In the endothermic reaction, what happens? The reactant takes in heat from the surroundings and we are getting product. How does the thing like? Reactant takes in heat and it forms a product, right? Now over here we have to draw the enthalpy level diagram. So this, right? Now what is activation energy? EA? EA is the reactant to the top of the hill, right? Is it clear? Reactant to the top of the hill, right? So this to the top of the hill, this, right? This. So reactant to the top of the hill is the activation energy, right? Remember always. Now what is delta H? Delta H will be reactant to the product, right? To the product, right? Something like this. Reactant to the product will be this, right? This, you're getting this? Reactant to the product. This is delta H. Always reacting to the product. So over here in the endothermic reaction, what happens? We are seeing that energy of the reactant is less than the energy of the product of this thing, right? And whatever energy is less, that substance will be more stable. So in endothermic reactions, reactant is more stable. Just remember this thing, whatever energy is less, that substance will be more stable. In the exothermic reaction, we are seeing what? The energy of the reactant is greater than the energy of the product. So who is more stable? The product is more stable, right? More stable, because whatever energy is less, that is more stable. And in the endothermic reactions, the reactant is more stable over here, right? So this is very important portion we learned, right? Now come to the part called as whenever you're giving heat to a system, right? Whenever you're giving heat to a system, the first thing you have to learn is that the temperature change depends upon what? Depends upon an equation. Q is equal to mc delta T, right? Isn't it? Whenever you're giving heat to a system, the system's temperature increases. And how does it increase? It increases by a very important parameter that is called a specific heat capacity of the system, right? So we can learn that Q divided by mc is equal to delta T, right? So we know that if you're giving this, if you're taking wood, 1 kilo wood, 1 kilo iron, and 1 kilo silver, isn't it? We are giving the same amount of heat to all these 1 kilo wood, 1 kilo iron, and 1 kilo silver, right? The temperature change will depend. See, we are making this heat and this mass control variable, right? The temperature change of this system will be depending upon what? The specific heat capacity, right? This. Now tell me, Celia, if the specific heat capacity is more, the temperature change will be less or more? Celia, can you hear me? If the specific heat capacity is more, the temperature change will be less or more? Tell me.
More.
See, if the specific heat capacity is more, see, it is in the numerator. See,
Oh, yeah.
this will be less, right?
That's
Now, K, tell me, if the specific heat capacity is less, the temperature change will be more or high?
higher.
Higher, isn't it? So this is a very patent question you'll be getting your boards, right? Questions such as like this, right? Suppose I'm going to this page, this will be 217, I guess. Yeah, yeah. See, you're getting this question, right? See, 500 joules of heat is added to 100 kilograms of the sample, gold, silver, copper, and water, right? Now the equation we have to use what? Q is equal to mc delta T. Q divided by mc will be equal to delta T, right? Isn't it? Fine. So now can you tell me the answer? K? What's the right answer? Highest temperature change, right? Which answer? Tell me. Okay. Okay. What's your answer? See, the Q is the same. We are adding same amount of heat to gold, silver, and all. Same mass you have taken, right? The temperature change will be depending upon the specific heat capacity, C. If the C is more, numerator it is, so dividing, larger value dividing, the temperature will be smaller, right? If the C is less, the temperature change will be more. They're asking you the largest temperature change. What is your answer? Can you just guide me, Celia? What's your answer, Celia?
My answer is gold.
Answer is gold, you are saying. This is Celia. What about you, K? K? What's your answer, K? Kavya, what's your answer? Kavya? Kavya, can you hear me? Kavya, what's your answer? Hello? Kavya, can you
Yeah,
hear me? What's your
yeah.
answer?
I think C. No,
C.
wait. A, my bad.
A, right? Okay. Okay. K, can you hear me? What's your answer?
A.
A. Is it clear to you? This is a common question of the boards, right? Now, first thing I'm telling you that we have to know about the what do you mean by standard conditions, right? K, can you tell me what do you mean by standard conditions? See, we are seeing that we have used delta H dot and delta H without dot. What does standard condition mean? Standard condition means what? Means we are taking pressure at 100 kilopascal. See, standard conditions in the SHE standard hydrogen electrode. Remember, 100 kilopascal, temperature should be 298 Kelvin, and the solution should be having a concentration of 1 mole per dm cube, right? These are standard conditions having, right? Isn't it clear to you? So this is very important for us to understand that whenever we are seeing standard conditions 100 kilopascal, 298 Kelvin, and all solution should be at 1 mole per dm cube. First thing we have to understand is that we have to see that whenever we are seeing the combustion, enthalpy of combustion is what? When 1 mole of the substance is completely combusted in excess oxygen under standard conditions, under standard case, right? What is standard enthalpy of combustion? Standard enthalpy of combustion is the enthalpy change when 1 mole of the substance is completely combusted in excess oxygen under standard conditions, right? So how do you find out the standard enthalpy? We find out the standard enthalpy by the calorimeter. In the calorimeter, we do what? In the calorimeter, we are taking the substance to be combusted, ethanol, in the burner. Suppose we are taking 0.98 grams, 986 grams. We note down. We're going to find out the standard enthalpy of combustion of ethanol. What we do? We take a calorimeter with water inside it. We note the water, 500 grams, right? Isn't it? We put a thermometer inside it to note down the delta T. We take an assumption, let all the heat go from the flame to the water, right? Like this, flame to the water, right? If the flame is releasing Q amount of heat, water will also absorb Q amount of heat, isn't it? It will be absorbing Q amount of heat. And what happens? The temperature will be increasing. Can you find out Q? Yes, we can find out Q. How? Q is equal to mc delta T, right? We have to use this. M is what? M is the mass of water. C is the specific heat capacity of water. That is 4.18, right? 500 into 4.18 into temperature change. Suppose it's 10 degrees centigrade. We multiply this 10 degrees centigrade. We are getting the Q. What's the Q? Q is the heat which is given out from the flame to the water, right? We are getting Q over here, right? Fine. So we are getting what? Q is equal to mc delta T, right? So one at Q, we get Q in joules. Is it clear? We get Q in joules. When we get Q in joules, we have to divide it by 1000, right? To get kilojoules, right? Because delta H unit is what? Kilojoules per mole. We divide joules by 1000, we get kilojoules, right? Then we do what? We know that delta H is kilojoules per mole. So we have to divide it by the number of moles of the ethanol. Ethanol MR is what? 46, right? Divide by 46. Suppose we're getting X. So we divide X by Q kilojoules, right? We get delta H. Easy? Fine. So this question will be seeing that whenever we are taking the standard enthalpy of combustion, we are taking the combustible substance weighted in the burner. We're taking assumption that let all the heat go from the frame to the water, that is Q, and Q amount of heat is absorbed by water. Now we find out the Q by what? Q is equal to mc delta T. M is the mass of water, we pre-record it, and delta T we from the thermometer. We divide this by 1000 to get kilojoules. Then we divide by the number of moles of ethanol, right? Ethanol. We get what? We get the delta H. In this particular reaction, we'll be seeing that the delta HC we are finding out will be less, right? Will be less than the actual data. Suppose we are getting minus 1100 kilojoules per mole. The actual data of ethanol is 1367 kilojoules per mole. We'll be getting a less exothermic value. Why? You have to answer. The first cause of the less exothemicity is that we have taken an assumption that let all the heat go from the flame to the water to make our mathematical expressions easier, not complicated. We have to take over here that let all the heat go from the flame to the water. Now over here, we will see that whenever we are seeing the heat is less exothermic, right? Why? Because we know very well that some of the heat will be used to heat up the surroundings over here. Heat lost. Heat is lost to the surroundings. Number one. Number two, we are heating the copper calorimeter. The copper calorimeter will also release heat. Heat will be lost. See, is it clear? Heat will be lost, right? Finally, delta HC is what standard conditions we do, right? 100 kilopascal and 298 Kelvin. Our school labs is not pressurized lab where 100 kilopascal can be maintained. 298 Kelvin can be maintained. So we cannot maintain standard conditions over here, right? Isn't it? So that's the reason we are getting what? We are getting a less exothermic reaction, right? See, let's send me a message. Delta HC, worked example 219. Do this worked example, right? Isn't it? See, it's very easy. It's very easy. It's very easy. Q is equal to MC delta T. Mass of water is this. Specific heat what is 4.18. Delta T is what? 13. Then we get joules. We divide by 1000. We are getting kilojoules. Then we divide this by number of moles of ethanol burned, right? See, 0.45. We divide by 46. We divide this by the number of moles. We are getting this, right? And we are getting less exothermicity. If you have got your book, please open your book quickly and mark this importance. Why there is less exothermic? See, we are getting a less exothermic because heat is lost by the flame to the surroundings, right? Isn't it? And the ethanol combustion is unlikely to be complete, right? Because limited supply of oxygen is there, right? Now, this is the thing we learned, right? Enthalpy of solution, I'll be sending the page numbers for you to do. Now, come to the part called as formation enthalpy. What do you mean by formation enthalpy? Now, okay. Now, see, if you see that what is meant by formation enthalpy? Now, enthalpy of formation is nothing but it is an enthalpy change. When 1 mole of the compound is formed, where is 1 mole? 1 mole of the compound is formed from the elements, right? Elements is what? Cl2. Now we cannot change 1 mole over here, remember. We cannot change 1 mole, right over here. What we do? We have to equate this equation. We put half over here, half Cl2, right? Isn't it? So this is the enthalpy of formation equation. What is the enthalpy of formation? Enthalpy of formation is the enthalpy change when 1 mole of the compound is formed from its elements in the standard state under standard conditions, right? We cannot change over here. 1 mole we cannot change over here, right? So we put half over here, right? Enthalpy of formation is very important, right? Because we have to use it in Born-Haber cycle also and is lattice enthalpy also, right? Now see, now